This is Daryl with Hands-On Cisco Training, episode 18. Today we're going to talk about OSPF stub areas and neighbor synchronization. It's the 22nd of September 2007. My feed remains on SwitchPod. However, .Mac now supports personal domain names, so my website, you can still get there at the old link, but the new link is www.darylroot.com. My email address is ciscotraining@mac.com. And now that iWeb from Apple supports Google AdSense more easily, I've put some Google ads on the page, and you can support these videos for free by helping to improve my Google PageRank by linking your website to mine. So I would appreciate if you like these videos, if they're useful to you, I would appreciate your support by creating a link, and it's free for you and it helps me out. So today I have a book recommendation, Routing TCP/IP Volume 1, 2nd edition by Jeff Doyle and Jennifer Carroll, and I did use it while reviewing material preparing for this video, so my thanks to them and Jeff Doyle particularly for the 1st edition, which was instrumental in helping getting me my CCIE certification back in 2001. Okay, let's look at our network for today. Here is our triangle, and it's the same triangle as the last episode. The middle router and the bottom router are speaking RIP to each other. The RIP area is in purple. The middle router is speaking OSPF to the top router in area 0. The middle router is an autonomous system boundary router because it is redistributing from RIP version 2 into OSPF. The top router is in 2 areas, so it is an area border router, or ABR, and it's in area 0, and it's in area 172.16.6.0. And the top router and the bottom router are speaking OSPF in area 172.16.6.0. Keep in mind, however, the bottom router is not redistributing from RIP into OSPF. So if you are in the OSPF area and you want to ping 172.16.3.1, the only way to get there from from an OSPF router is well, strike that. In any event, let's move on. Let's go ahead and take a look at the bottom router. In the bottom router, here is our OSPF configuration. We have network 172.16.6.2 0000 area 172.16.6.0. So let's look at that on the map. And here is 172.16.6.2. Our don't care bits are 0000. So this is turning on OSPF on that serial 0 interface, which means that we're speaking hellos on the serial link and we'll form a neighbor relationship with the top router, and it's in area 172.16.6.0. Let's go ahead and look at our routing table. Our routing table, we have our 3 directly connected subnets. We have 2 OSPF inter-area routes for 170.16.1.1/32, which is the loopback of the top router. Now note, the loopback of the top router is really a /24. However, OSPF treats all loopbacks as stub networks and just injects a and just has a /32 in the route table. And then we have 170.16.2.0/24. It's also an OSPF inter-area route. And that is for this subnet. And then what's interesting is 170.16.3.0/24, it's an OSPF route, it's external type 1, that's the route for this loopback. Now in the bottom router, we're running RIP and we're running OSPF, and we receive the route via RIP and we receive the route via OSPF, and the question is which way. We receive the route via RIP and we receive the route via OSPF, and the question is which way do we prefer? Well, OSPF has a lower administrative distance than RIP. You can see here in the route table that the administrative distance of OSPF is 110, which is more believable than the than the administrative distance of RIP, which is 120. So our router has a choice of the RIP route or the OSPF route to put in the route table, and it puts the OSPF route in. Okay, let's look at our Ospf database. And in our Ospf database, this router is just in, this is the bottom router. It is just in area 170.16.6.0. There are two routers in that area because that area consists of the red area here, which means that the top router and the bottom router are only two OSPF routers in that area. The middle router is in a different area, and router LSAs are only flooded within an area. And then we have, so within there, we have the two router LSAs. We don't have any network LSAs because all of our links are point-to-point. Network LSAs are used for Ethernet broadcast networks, for example, where you can have 4 or 5 or 6 routers hanging off of one Ethernet hub. We have two summary network link states. These are routes that are injected into area 172.16.6.0 by the top router, which is an area border router, and one of them is for the loopback, and one of them is for the serial link. And so we have two summary network link states, and then we have one summary autonomous system boundary link state, which is for this loopback over on the middle router, because this loopback is getting redistributed into OSPF by the middle router, and then that gets then the summary autonomous system boundary link state gets flooded. Oh, I'm sorry, I misspoke. That's the summary autonomous system boundary router link state. So there is one autonomous system boundary router in our network, one router that is redistributing from another routing protocol into OSPF, and that is the middle router. And this is the LSA which tells you how to find that router. And then that router is actually redistributing 3 routes into OSPF. It redistributes the RIP route it's redistributing RIP, and there are 3 routes in the RIP area. This loopback, this serial link /24, and this loopback /24. So all 3 of those RIP routes get redistributed into OSPF, and in the external LSA, which is type 5, we have 3 LSAs for those 3 routes, and it tells you what the advertising router is. And the way you add this to your route table is the OSPF process knows, okay, here we have these 3 external routes, and we know what autonomous system boundary router is originating that route. And then OSPF knows how to find the autonomous system boundary router thanks to the type 4 LSA, summary autonomous system boundary router LSA, which is up here. So you know the route. You know to get to the route, you need to get to the autonomous system boundary router, and to get to the autonomous system boundary router, you have that information here of how to get there. Let's look at a route table then. Now, we had 3 external type 5 LSAs for 3 RIP routes that were getting redistributed, but only one of those LSAs was entered into our route table. And the reason only one of them was entered into the route table is because this is on the bottom router, and I have a choice for, let's say for this serial link here, this /24, I have a choice. I can go to that network via the OSPF external route that I received from the area border router, from the autonomous system boundary router, redistributed from RIP, or I can go to the directly connected /24. Well, a directly connected route has an administrative distance of 0, which is much lower than the OSPF administrative distance of 110. And so we prefer the directly connected route to the route we received through the routing protocol. And that makes sense, because why go off 3 or 4 hops away when you're directly connected to that subnet anyway. If you're directly connected to the subnet, just deliver the packet to that subnet, because that's what we're talking about here. We're talking about delivering packets to subnets. Okay. Let's go ahead, and we wanted to talk about OSPF stub areas today. So let's make our area a stub. So conf t router OSPF1 area 172.16.0.0 I'm sorry, 172.16.6.0, which is our area identifier for this stub. And there we are. I made it a stub. Let's see if any log messages pop out. Ooh, I got a problem. My OSPF neighbor is down. So I see a neighbor, but the state is down. And why is that? Well, let's do a debug and try to find out. Debug IP OSPF adjacency. And we'll stand by for a few seconds. And there we got a useful message. No debug all. So we received a hello. OSPF routers advertise hellos. They send them out OSPF enabled interfaces. And other OSPF routers receive those hellos and they process them. And if the hellos have matched information regarding the area and particular types of flags, then the OSPF routers will become neighbors. In this case, we used to be a neighbor, and then I've received a hello from the other router. It says it's area 172.16.6.0, which matches my area, so that's good. We received it on our serial 0 interface. The router ID was 172.16.6.1. That's the router ID of the top router that sent us the hello. And then we have another log message. The hello had a mismatched stub area option bit. And that makes sense. I just configured stub on the bottom router. I have not yet configured stub on the top router. So OSPF will not form a neighbor. Now this is important because stub areas improve the scalability of OSPF. But to migrate to a stub area, all routers in an area must be stub. And as soon as you enable stub, guess what? On one router, well, guess what? It refused to form a neighbor relationship with the other routers. So this is an impacting change. If you want to convert an area from non-stub to stub, you have to plan for an impacting change or use some other mechanism to get the packets to the destination, because as soon as you configure stub on a router, it's going to be mismatched from the other routers in that area, and all the neighbor relationships will go away. And so now if I try to ping 172.16.2.1, it worked. Let me try to figure out why. Okay, I am learning that route via RIP from my other router. Let's go back and look at the route table. If you remember, I did not have any RIP routes before, and now I have RIP routes. So we have lost our OSPF routing information. However, the middle router is still advertising all of its directly connected routes in RIP, and I'm receiving it at the bottom router. And the packet I was pinging happened to be in that area. Let me try the pinging 172.16.1.1. Again, I cannot ping 172.16.1.1, which I was only learning via OSPF, because on the bottom router my OSPF neighbor relationship is down, so I don't have any useful OSPF information anymore. So that's, yes, I have a network outage in progress because I configured stub on one router in an area, but not on all the routers in the area. So let's look at the OSPF database before I go and fix this. Show IP OSPF database. I still have all, this is interesting, I still have all of my LSAs. I don't just throw away the LSAs because I lost my neighbor relationship. I still have the LSAs. I'm just refusing to use them because I don't have a neighbor relationship with 172.16.1.1. So even though I know that 172.16.1.1, that router is connected to various subnets thanks to this router LSA, since my neighbor relationship with them is down, I'm just ignoring the LSA and not entering those OSPF routes into the route table because something's obviously broken here. Okay, I'm over on the top router now. Let's do some debugs so we can see the neighbors come up. Debug IP OSPF adjacency. And let's T router OSPF1 area 172.16.6.0 stub. And let's see if my neighbor relationship comes up. The hellos go back and forth. I think the default is every 10 seconds on hellos. And I got a ton of stuff. No debug all. Okay, let's go back and look through the OSP, look through what happened. I configured the area as a stub. I'd previously configured area 172.16.6.0 as a stub in the bottom router. Now I've configured it at the top router. So our area numbers match, our flags match, because stub is a flag in the hello packet. And so let's see what happens. So we received it, because I was just doing the OSPF adjacency events, I believe I received a hello, but it didn't show that up in the debugs because I needed to run a different debug to see that. So I received a hello, and then I received a database description, and we went to state init. And then we went to state two-way. We received two-way communication, so we went to state two-way. And then we started sending database description information to them. And then our neighbor negotiation is done. So we're going to become a slave, and I'm telling you a lot of words that I haven't explained yet. And then we started sending our database description information, and we move into state exchange. And once we exchange all of our database information, which means all of the LSAs, the whole goal here is to synchronize our LSAs. Database request sent. We send a request for specific LSAs. We're still in state exchange because we're receiving database descriptions. And then exchange done. And still exchanging database information, and then we're synchronized and our state goes to full. And then we see this log message, which is OSPF process 1. We have a new neighbor, neighbors 172.16.5.1. We went from loading to full and loading done, so we became neighbors. Let's talk a little bit about what that means. To form an OSPF neighbor relationship, OSPF routers send hello messages to discover neighbors. These hello packets include all OSPF routers already seen. So if I'm on the bottom router and I'm sending an OSPF hello packet out this interface towards the top router, and I've already seen the top. If I have not yet seen a hello from the top router, I just send it with my information. But then the top router receives that hello, and it'll send a hello. But its hello, it'll say, hey, I see router ID 172.16.5.1 out this interface. And that way, when the bottom router gets back the hello, it'll have its own router ID in there. So at first, when I'm just sending in the hello without having seen, at first the top router, it received the hello, and that hello did not have its own router ID in it. And so that's when you go to init state. And then later, after the hellos have gone back and forth, the bottom router says, hey, I see you, top router. I'm going to put your router ID in my hellos just to let you know that I see you. And that's when you go to two-way state. So you start with with down, which I actually didn't write here, but I'll write it right now. down. You start in the down state, or not even knowing the neighbor exists. And then you go to a init state where you've seen a hello packet from another router, but that hello packet did not have our router ID in the list of known neighbors. And then later you see hello packet with our router ID, and that means that two-way communication is working. So that's why they call that state two-way. And then you exchange information about which LSAs are in your database. You're basically given the table of contents for your LSA database, what LSAs you have, and that's exchange start. And then the routers, they figure out that they need LSAs from each other, and they send requests for those LSAs, and they get those LSAs, and that's the exchange state. And then after the exchange state, there is a loading state, and I'm not sure exactly what that is. I think that means you've finished exchanging the LSAs, and you need to calculate all of the routes based on that information. And then you go into the full state, which means we've exchanged all of our LSAs, we've calculated all our routing information, routing is up and stable. Okay, great. So let's go back and look at our debug again. We received the, we're not showing the hellos here. We received a database description, so we move to state init. And then we receive another hello with our own router ID in there. So we receive a hello from 172.16.5.1 and has our own router ID in the list of routers they've seen. So that means two-way communication is working, so we move to state two-way. And then we start sending database descriptions to each other, and we go into the EX start phase, and it's not listed here, but part of the EX start phase is you decide who is the master and who is the slave, so who's going to control the LSA exchanges. And then, so we've exchanged our inventory of LSAs, and then we move into the exchange state, which is, hey, let's send LSAs back and forth. And so we're sending LSAs back and forth. We're sending our database descriptions. We sent a database request to, which is an LSA request to, we receive the databases back. We're still in the exchange state, and then exchange is done. Hey, we've exchanged all of our LSAs. We send our database description. We just verify that we're synchronized. Our state is full, and oh, by the way, we need to load our routes into the routing table, and I believe that's what loading is referring to. And then, once we're done, we have a new neighbor. We have a new router neighbor, so we have to update our own router LSA, so we do that, and then we flood it again. So that's the ironic thing. You exchange all of your LSAs, and then when you're done, you have a new neighbor relationship, so you have to change your own router LSA, which means you need to flood it again. Okay, so that is neighbor synchronization in OSPF. But you know what we did is we went and configured it as a stub area. So let's go and see what effect we have, because we have not actually talked about what a stub area does. So I'm back on the bottom router. Show IP route. Let's see if there are any changes in our route table. Okay, this is interesting. Before we configured as stub areas, we had 3 connected routes. We had 2 OSPF inter-area routes, and they're all still there. And we had a OSPF external route for 172.16.3.0/24. But now we have a RIP route for that, and we have an OSPF inter-area default route from 172.16.6.1, which is interesting. What's going on here? Well, let's talk a little bit about what an OSPF stub area does. A stub area decreases the need to send external LSAs into an area. If you redistribute 1,000 routes into OSPF, then you have 1,000 external Type 5 LSAs in your OSPF area, and that can be a significant level of CPU. That can be a significant use of resources. So you want to stop it. A stub area basically says, hey, anywhere you are in the stub area, no matter where you want to go, if it's outside of this area, just go to the nearest area border route. And so what do you call a gateway of last resort? You call that a default route. So what happens is the area border router, which is 170.16.6.1, will inject a default route into the OSPF stub area. And that means that you don't need to inject any external LSAs, because if you don't know how to get to your specific destination, you'll just follow the default route to the area border router, and the area border router will know that information. So looking at the picture, because this is a stub area, and the top router knows it's an area border router, and it knows it's an area border router because it has interfaces configured on 2 areas, it injects an LSA into, it injects a default route into area 170.16.6.0. And then the bottom router, if it needs to get to a route that was previously external, like 170.16.3.1, it will follow the default route to get there. In our case, it's a little bit more complicated than that, because our router has the choice of the default route or the RIP route. Because 170.16.3.0/24 is also in RIP, and our router is also in RIP. That's a little bit of an extra complication given our lab environment where we're trying to do this with only 3 routers. So here's the quick trivia. Here's the question for you. What's more believable? A RIP route for 170.16.3.0/24 with an administrative distance of 120, or an OSPF default route with an administrative distance of 110? Well, you might think that the lower administrative distance is more believable, but remember, more specific always wins. A /24 is always more specific than a /0. So even though we have a default route that is an administrative distance of 110, we will still follow the more specific route for via RIP, and that's why the RIP route ended up in our routing table here. Okay, back to the stub area. Let's go ahead and look at the effect on our Ospf database. So IP Ospf database. We're a stub area. We still have 2 routers in our area, so we still have 2 router LSAs. We have 3 summary network LSAs, which are, these are type 3 summaries that we get from other areas in OSPF. And an OSPF stub area has no effect on the summary network LSAs. It only has an effect on the type 5 autonomous system external LSAs. But look at this. They're still there. I thought they were supposed to be gone. I'm going to pause. These LSAs are now 1,400 seconds old, and I'm going to pause the recording for a while so that we can see what happens when these age out. And we're back after waiting a while. You can see here that the OSPF external link states have an age of 3,552 or 3,553 seconds. And then I'll hit refresh. 3,569 seconds. So we're almost to the 1 hour mark. And OSPF LSAs get reflooded periodically, and then they expire after an hour. Now, all of the other LSAs have been reflooded, and so they have a lower age. But the external LSAs and the external summary LSAs type 5, and then the autonomous system boundary router summary LSAs, which are type 4, have not been reflooded for quite some time. I'm back after a little while longer. You can see I was expecting the LSAs to age out after 3,600 seconds, which is 1 hour. And as you can see, the LSAs lasted longer than 3,600 seconds. So at least these external LSAs lasted slightly longer than 1 hour. However, now, a few minutes later, they're gone. So the LSAs, so when we created a stub area, the area border router stopped flooding the type 4 and type 5 LSAs into the stub area, which is as we expect. In a stub area, you don't need the external LSAs because you don't need any external routes. Instead, you just follow your default route. So creating a stub area does improve your scalability in the area because that area does not need to have all the external LSAs, and there could be thousands of external LSAs. However, it doesn't happen instant. The LSAs don't just go away. Creating a stub area doesn't make any LSAs that are already there go away. They just age out after an hour. And let's look at our routing table. And our routing table is as it was before. As soon as we created the stub area, it changed to this configuration where we have our connected routes. We still have our inter-area routes, but we do not, because we have our summary type 3 LSAs, but we do not have any external routes. Instead, we have this default route, which points back to the area border router for our area. Okay, so just to review a little bit more. We were talking about OSPF stub areas and neighbor synchronization today, and we showed the effects of creating a stub area, and we showed the steps in becoming OSPF neighbors. That's it. Thank you.